All right. So today, what we're going to discuss in this session about the VPN. So this is the first class of the VPN. So first, we have to understand what is the objective of the network security, and why exactly the VPN, the types of VPN. In that particular, we'll also discuss site-to-site VPN. In site-to-site VPN, we'll discuss about the aggressive mode. We'll discuss about the main mode. Before that, yes, we'll be also discussing about the phases and different the objectives of the security. Okay, so as you see here in this particular document, what we're going to understand, what are the network security objects, right, that we are working on to secure our network. So as you see here, the confidentiality is the one part that we have to work on. What is confidentiality exactly? If someone asks what is confidentiality, so what will be your answer? So your the confidentiality is exactly that the data is being accessed by the authorized individual or the systems. Means authorized person, as well as you are using the authorized maybe company provided laptop or any desktop that you are using for maybe sending an email or accessing some servers, any services. All right, so the confidentiality means here that the data is being accessed or used, all right, by the authorized individual or the systems who can view the sensitive information, who can make changes on that sensitive information, right? That is called confidentiality. So there are, if we talk about the data, in normal way, so there are two types of data actually, and this is what we are protecting for, right? So that our data should not be compromised, and it should not be shared. So there are two types of data. One is the data in motion, so that's kind of a very basic of the security, and the other is the when the data is sitting on the storage media. So data in motion means when the data is traveling, when you are accessing the data is going to the network, right? um, and the other type of data is like we have the storage servers. On those servers we have the important files stored. Could be the, let's say, TFTP server, which is very commonly we use in our industry, in our production. So we deploy on TFTP server where we have all the sensitive data, maybe softwares, maybe some documents, confidential documents, and these are the two types of data, what I'm trying to say. So confidentiality is one of the network objective, and we have to make sure whether the data is in motion or data is sitting in on storage media. Both have to be accessed. If you are accessing any of the type of data, it has to be authorized, individually. It means it should be the individual who is authorized to access or to view the data, as well as that system, right, what you are using to access the data should be also authorized. The next is integrity. Integrity is something that what are changes, right, being done by the, again, in the individual or the systems, right? So changes, what kind of changes you're talking about? The changes, I have to make sure that I have, let's say, send an email to from my laptop from here, right? And I have to make sure that this particular email should not be altered anywhere on the transit. So once I click, hit on send button, so obviously that email is sent from my computer. Now there should not be anywhere on the transit in between where someone hacks that particular email, make the changes or captures it, right, make the changes and then send it to the destination. So integrity means the data should not be altered. This data should not be disclosed anywhere in the transit. uh, Third is availability, right? So availability is something, those servers which we are using in production should be always available for our employees, for our internal use, for our customers use. Think of, any website, or Google website itself, let's say. Uh, what if the Google website itself is busy, where what all you are searching, it is taking half an hour to display the the result. So which means the Google server is not available for the users, for the public users, for the private users. So we have to also make sure that this availability is of the servers, of the storage servers, internal servers are always there for our employees, for our customers, right? Which can be engaged using by denial of service attack. So these are the network objectives. All right. I'm not going to discuss all those, but if I say cost benefit analysis of security, so we have like asset, which is hold on guys, one sec. All right. So after discussing particular the objective of the network, right? Let's discuss which is the main topic of today's session. Understanding the VPN technology, understanding the VPN cryptography. All right. So what is the VPN, and what is the uses of the VPN? So as you see here, the VPN is nothing but virtual private network. What does that mean? So virtual private network means the two companies or the two branches are communicating to each other over the untrusted network. So it is like I am creating the virtual session between two endpoints, maybe branch 1 and branch 2, right, over the untrusted network. So untrusted network means both the branches are connected to the service providers, right? And so let's say over here, this is maybe a head office, this is maybe a branch, and we have here, this is a cloud, right? Here I have internal network, and here we have internal network, and this is the cloud where we are connected to, right? And this is HQ, head office, and this is branch, could be branch 1. So in this virtual private network is what all data we are sending across this particular ISP or to the untrusted network. I have to make sure that there is one virtual session created between two endpoints between them, okay, and makes a private network. Means this particular session, this tunneling mechanism, what you can say, is used by no one else. It's like only the company is using particular this session or the tunnel over on this untrusted network. So now this particular ISP is not aware of what these branch offices are exchanging, right? Even if we have a hacker over here who is sitting maybe on an untrusted network and trying to hack the data, they may get successful to hack it, but they won't be able to check what exactly we are transmitting, what IP addresses we are using, what data we are sending, right? That's the whole logic of the VPN, right? So as you see here, the word virtual refers to the logical connection between two devices. For example, one user may be connected to the internet. These are the examples anyways, and other user may be connected to the internet, right? And we could build a logical network or virtual network between the two devices using the internet as our transport mechanism. So here what we are using internet to transport our data, right? And making making virtual connections. That's what it is called, the virtual private network. All right. Types of VPN, if we talk about, we have IPsec, we have SSL VPN, we have MPLS. We will be talking about the IPsec initially. Okay, so as you see here, the implementing security of IP packets at layer 3 of the OSI model and can be used for site-to-site VPNs and remote access VPNs. So this particular types of VPN, there are multiple types of VPNs, right? Where you are not using the layer 3 addresses as well. You are using, as you see that this SSL, where this secure socket layer implementation. It uses actually the TCP session at layer 4 of the OSI model. IPsec, it uses the layer 3 IP addressing, right, to form the particular VPN between two endpoints. SSL, it uses layer 4 between two endpoints, right? Same way MPLS, it uses the layer 3 VPN, right? It is normally called as an the 2.5 also layer. So it works on multiple layers, you can say. We'll be talking about that. Benefits of VPNs. So we have like remote access VPNs. Okay, so some users might need to build a VPN connection from their individual computer to the corporate headquarters. So remote access VPN example is I'm sitting here in at home, and I want to access some internal website of my company, where that those internal sites are only available for their employees, right? But by sitting here at home, I cannot access those particular sites, because in order to access, I have to go to the office, get connected to the office network, and then only we can access those sites, right? So here remote access VPN, where we can get connected to the through the VPN to our company network, remotely, and then probably we can access the internal sites, what all sites we want to access. That's something remote access VPN. We have also DIM VPN. We have also dynamic VTI, static VTI. We'll be discussing more about it in later chapters, in later sessions. But if you talk about here the main benefits of the VPN, what we are going to achieve using VPN, right? Confidentiality we have discussed, in data integrity we have discussed, authentication. What do you mean by authentication? Authentication means whatever data we are handing it over to, we have to make sure that the second party, my peer, right, my neighbor, is the valid user. So if I am, let's say, exchanging the data between two endpoints, right, so I have to make sure that both the users or both the endpoints are the valid endpoints. So that is where we have the authentication. In order to maintain the authentication, we have pre-shared, we have certificate authority, we have digitally assigned authentication. Again, we'll be talking about a bit more about this. Anti-replay. Anti-replay means we don't have to, so whatever data we are sending it to the untrusted network, right, to deliver it to our branch office, we have to make sure that the data is not being duplicated. No one, the hacker, even if it hacks, the hacker should not be able to duplicate it, right, and send it to the actual peer, right? So that's called something anti-reply. So maybe if I'm sending A, B, C, D, right? So it is not like that in between someone is creating a duplicate of it and then sending it to the destination. That's something called anti-reply. We should also understand about the cryptographic basic, the components, where we should understand what are the cipher and keys. So in this, what exactly ciphers? What is the role of the ciphers and the keys? We'll discuss, in detail probably. So if you talk about the ciphers, what is cipher exactly? So a cipher is nothing but a set of rules, which can also be called an algorithm. So we keep on hearing the word algorithm. This is exactly called cipher also. So it is a set of rules, right, about how to perform the encryption and decryption. It's called the algorithm. It's called the ciphers. So encryption and decryption means what encryption mechanism we are using at particular sender side, and what mechanism I have to use to decrypt it at the receiver side, right? So that is something called the ciphers. What is about the keys? The key refers to an instruction for how to reassemble the characters. Okay, so the key means what are keys. Normally we will be talking about the public keys and then the private keys. Okay, but it is, yes, it is kind of instruction how to reassemble what all segmentations you have received, or how to actually reassemble it, all those characters. So we'll be talking about the keys more. There are two types of ciphers or the algorithm, block and the stream ciphers. Okay, so encryption algorithm can operate on blocks of data at a time, or bits and bytes of data based on the type of cipher. So what does it mean? It means it can be this algorithm, let's say an encryption algorithm can be used, right, based on the data at a time or bits of the data or the bytes of the data. So let's discuss about this. So what is block cipher? Block cipher is a symmetric key, means the same key, this is the key point, same key to encrypt and decrypt. Okay, that is called a symmetric key, block cipher. So cipher that operates on a group of bits called a block. So block means a group of bits here will be used to encrypt, and the group of bits will be used to decrypt the data. We'll be discussing, as you see here, the example of symmetrical. So what all algorithm or the end protocols or the mechanism that we are using for encryption, right? So as you see here, we have advanced encryption standard, which is AES. We have triple digital encryption standard, which is 3DES, right? And we have the blowfish also. So these are the examples of encryption. These are the end mechanism that we will be using for encryption of the data. So either I will use AES or I'll use 3DES, right? There is a difference. AES is more secure. It takes longer time, but it is secure than the 3DES, right? We have the digital encryption standard, DES, international data encryption algorithm, IDEA. Normally what I have seen actually, either AES or the 3DES being used for the encryption. Let's discuss about the stream ciphers. So we discussed just now about the blocks, ciphers, where the group of bits will be used for encryption and for the decryption, and the same group of bits will be used for encryption, and the same what you have used to encrypt, the same group of bits will be used for the decryption also. Stream cipher is a symmetric key, again, same key to encrypt as decrypt here, but where each bit of plain text data to be encrypted is done using one bit at a time against the bits of the key stream, also called a cipher digit stream, right? So what does that mean? That means here also the same key will be used for encrypt as well as to decrypt, right? But it will be against one plain text data to be encrypted, to be encrypted is done using one bit. So it is like corresponding one data and then one bit. Okay, so it is like if you have two plain text data, in that case we'll be using 2 bits, 3 bits, like that. Okay, this is something symmetric and asymmetric algorithm. So since we were discussing about here the symmetric keys, what is symmetric exactly? So now a little clearer here. So symmetric encryption algorithm, also known as symmetrical cipher, uses the same key to encrypt and the data and to decrypt it. So these are the examples here, like DES, 3DES, we have already discussed about it. Asymmetric is something, example of a symmetric algorithm is the public key algorithm, right? So what do you mean by the public key? So it is like, as I told you before, there are two types of keys. One is the public key and the other one is the private key. So the public key is basically given by whom? It is given by the certificate authority. So the public key will be given by the certificate authority to both the peer, okay, and then it will be used. So that using that public key, I will be sending the data. So once my peer receives that data, peer will get to know that using the public key that okay, this particular user is the authenticated, right? So that's something called the public key. yes, the private key is something. So every company, every peer will have their private keys. So what private key I'm using here, the same private key also will be used to decrypt the data there, right? So that's something about the VPN, about this particular symmetric as well as the asymmetric. Okay, so let's talk about the hashing, because what we have discussed as of now is the confidentiality. All right, what about the hashing, or what about the integrity? We have discussed about the integrity also, right? So hashing is a method to use to verify data integrity, right? So a cryptographic hash function is a process that takes a block of data and creates a small fixed size hash value. It is one-way function, right? So what does that mean? Means I have the raw data, all right? I will encrypt it using some hashing algorithm like message digest, secure hash algorithm SHA-1 or 2, right? By adding some additional bits on that. Okay, so more bits you are adding to it, to your actual raw data, it is more secure, right? The data integrity is more secure, more. Yes, it will take time, it will take more time to decrypt it as well, because more bits you are using to encrypt it, right? It will be taking a little more longer to decrypt it also. So the more bits you are using, it will be a little slower, but yes, definitely it will be secure, right? So for the data integrity, what we use is the hashing, right? So what we have to understand here, for the confidentiality, what we are using, for the hashing, for the integrity, what we are using, right? And further for the authentication, what we are using. So we'll discuss about that also. uh, in the hashing, we have also the hashed message authentication code also, which is called HMAC. It is also being used nowadays. This is kind of advanced hashing mechanism also. So uses the mechanism of hashing, but it kicks it up a notch. Instead of using a hash that anyone can calculate, it includes in its calculation a secret key of some type. So uh, normally what I have seen, either MD5 or the SHA being used. Here we have SHA 2, 3 as well as 4. We have up to 16, I believe. So we'll talk about that more once we are into the configuration. All right, we were talking about the digital signatures. This is digital signature is used for the authentication. Okay, but how digital signature is, and who provides you the digital signature? So when you sign something, it often represents a commitment to follow through, or at least prove that you are who you say you are. In the world of cryptography, a digital signature provides three core benefits: authentication, data integrity, and non-repudiation. What does that mean? So it means digital signature is something. I will give you one example. So let's say you are driving, right? And the cop actually uh, catches you driving. So in order to authenticate you as that you have the authority to drive the car, right? What cop will be asking for your driving license, right? So when you show the driving license, the cop now will be checking on that driving license. Cop will be checking your image, that is it you that which is there in the driving license. So once it finds that yes, it is you, then corresponding it will be also checking whether this particular license has been given by the government or not. Means whether that particular license, driving license, is the valid or not, right? So these are the ways of checking, right? So similarly here, the digital signatures are being given by the certificate authorities, right? What is certificate authority? Nothing but the government approved. They will be the vendors who are authorized to provide the digital signatures. So for example, you can configure certificate authority as in Microsoft, server also. You can make one Microsoft server as in the certificate authority for the digitally signatures. There are other vendors also, but they are authorized in terms of providing the digital signatures, in terms of the providing the certificates, right? Uh, we will be talking, I'm not going to cover everything over here since we are going to discuss about the site to sites. We'll be skipping as of now because my main intention was to discuss about the VPN. So I'll be, yep, I mean, since we have discussed about the certificate authority, so let's discuss a little bit more about the certificate authority. What exactly certificate authority we have just now discussed, right? So it is like whosoever is certificate authority, we as an organization, we have to provide them the domain, our IP address, our user, right, to the certificate authority. Based on that certificate authority, the information provided by the company, they will provide you the digital signature, right? So I mean, as this is the also recorded session, so what it is written here, you guys can also, you can pause it and then probably just go with this. What all, the procedure that we have here in this particular, while enrolling your company to this, certificate authority, and how it is giving you the digital signatures, what all the overall process, that all you can actually, go with this, go through this. All right. So again, this we have already discussed: confidentiality, data integrity, authentication, as well as the anti-replay. We'll be discussing about this IKE, right? This is a protocol. Ipsec uses the Internet Key Exchange protocol to negotiate and establish secure site-to-site or remote access VPN, right? So IPsec itself is a protocol. Actually, it's a kind of umbrella of the protocol. It's a suite of the protocol in which there will be some other protocols also being used. So IK is what exactly is a framework. It provides the internet. It provides actually the Issac camp. Issac camp is again another protocol. So IK is a framework. Okay, inside this Issac camp, we will be having the Internet Security Association Key Management Protocol, commonly known as an Issac camp, and parts of two other key managements, other key managements also there, like Oakley and Secure Key Exchange Mechanism. So what we're going to use is this under this IK, right? So it's a kind of a structure. As you see here, IK is a framework provided by particular Issac camp, or it could be SKEME. So we're not going to use SKEME here because it is not used much. So mostly it is Issac camp only, which is used for the framework. All right. So IPsec uses two data structure to build the tunnel. All right. So when we are talking about the VPN, and we also talked about that we have to make sure that all four objectives, confidentiality, data integrity, authentication, and anti-replay, right? These four all mechanisms have to be, used in order to secure the, NPers as well as your data. So there's something called in this Security Association, SA, which holds encryption authentication parameters in each peer, right? For example, encryption and authentication keys. So the Security Association will be discussing about more. So it is when they are exchanging between two peers, right? When they are initiating this using the IK, or let's say Issac camp, when Issac camp is being used to initiate a session between two endpoints, then only this particular Security Association and SPI, which is Security Parameter Index, will be used. So SA actually holds encryption and the authentication parameters. SPI actually, it's kind of index where the field packet headed to select SA on receiver, just like we have the similar to VLAN or MPLS. So Again, under the SPI, it is like just like kind of holding the keys, what you are receiving from your remote end, from your peer. All right, when it comes to the negotiation, right? So when it comes to the negotiation, IPsec tunnel negotiation, what is the goal of IPsec? Goal of IPsec exchange is to establish essays between two endpoints. So if I have one router over here, another router over, so I have one router, another router, and this is a cloud. We have connectivity. So the goal here to exchange the essay, right? Exchange essay to establish, right? So IPsec actually uses two methods to encryption for the encryption: tunnel mode and then the transport mode. So we'll be discussing about that in a moment. But here initially, what we're going to discuss, so we'll be discussing anyways tunnel mode first, then we'll tell you what is the difference between tunnel mode and transport mode. So in the tunnel mode, right, this particular router is going to exchange the essay, right? It's going to establish essay, the security association between these two peers. So while establishing this session, there are two phases that it will be going through, right? So phase one, the phase one is the main goal of the phase one is to authenticate the endpoints. Means what this router is, which is from which is there in headquarters, and this is your branch. So phase one means only to authenticate these two end pairs, right? Means whether this particular router is the valid router or not. That is done under the phase one. All four things will be happening: confidentiality, integrity, authentication, right, will be happening here. Means I have to make sure that this particular end device and peer is the valid peer. That is the whole goal of this phase one, right? So they authenticate basically whether this particular endpoint is valid or not. While authenticating, I have to also make sure that what all authentication mechanism we are using, it should not be seen by someone else in the particular transit. So that is where we have the confidentiality. Means what all authentication we are using over here, it has to be understood by particular this router only, right? So in order to do that, we are going to use Issac protocol, right? So in phase one, which protocol we use? We use Issac. IK is just framework anyways. The protocol is going to be Issac protocol to establish Issac SA, right? And Issac SA creates a path for further negotiation. So once Issac actually declares this, that okay, this particular peer is the valid peer and the SA is established, then the next phase comes, which is phase two. So we'll be discussing about that more. But what exactly happens in this phase one? So IK phase one tunnel to succeed as follows, as you see here. Hash algorithm, we have to use either MD5 or SHA. A question, why do we use hash algorithm? Hashing we use for the integrity. Okay, encryption algorithm. Why do we use encryption algorithm? Anyone? For the confidentiality, right? What about the Diffie-Hellman DH group to use? So Diffie-Hellman group is something I don't want to use kind of a session where, you know, it is being compromised. Okay, so here the Diffie-Hellman group, what it will be using, it will be using the internal keys actually to be randomly used. So it is, see what happens when we set it up, it is like the same key will be valid, let's say for the 24 hours. Okay, so after 24 hours I have to use the another key. So it is kind of a pain. It is not scalable for the production that every 24 hours we have to use the different keys manually. So here Diffie-Hellman group is something that it actually sets the keys automatically, right? Yes, there will be, it is, I believe 24 hours is the default time. So once 24 hours is done, then automatically they will negotiate the another key. We don't have, without manual intervention. So we don't have to do anything with this, right? So that is where we use the Diffie-Hellman group. Authentication method. Authentication method is something whether the end user, whether the end peer is the valid or not. So that is where if I am setting it up, let's say the password over here in the particular one router in Cisco, and so in the other router also, whenever I receive the request, I should receive the request with this password Cisco only, which means that particular user is the authenticated valid user. So for the authentication, we are going to use the pre-shared key, PSK, and then lifetime. How long until this key phase 1 tunnel should be turned down, right? So what is the lifetime of the tunnel that the phase 1 should be up, and after that duration, maybe after that, once it is over, then it should go to the idle, or maybe you have to regenerate the traffic. That's something called lifetime. Right? Once the phase 1 is over and the SA exchange session is established, so as we discussed, the phase 1 is only used for the peer authentication. Now in phase 1, it has been declared that the peer is valid, right? Means whatever data we are handing it over to is the valid peer, is the valid user, right? Now we have to make sure, now after phase 1, what all data we are sending, okay, from what all data we are sending from, let's say this particular host, a machine over here sending a data. I'm sorry for this, it's a very bad machine. And machine over here exchanging the data, right? So what all data now it is, these machines are exchanging, I have to make sure that data is also encrypted, right? Data should not be compromised anywhere in this particular transit network. So that is where we have phase 2. Okay, so in phase 2, the entire conversation and the negotiation of IKE phase 2 tunnel are completely done in private because of phase 1 tunnel protection, the negotiated traffic. IKE phase 2 tunnel includes the hashing and encryption algorithm. So here in phase 2, I only need the hashing and encryption because the authentication is being already done in phase 1 itself. So it is already authenticated. I don't have to use the again authentication mechanism here. What I have to make sure, what all data you are sending from here, it is being encrypted, right? And added the extra bit to it so that it can change the identity of the data itself and send it to the untrusted network. So this IKE phase 2 tunnel is the tunnel used to protect the end user packets. Creates IPsec SA to transport protected traffic using the transform set. So that is what it means. So phase 1 to negotiate and authenticate the valid user, and phase 2 is to make sure that what all over the tunnel or over the session, what all traffic data packet is getting transmitted, it is secure, it is confidentiality is being maintained. All right, So let's go to the task. One moment, and see what we have to discuss there. Um, all right. So in the tunnel mode, in the because we discussed there are two types of tunnel. One is the tunnel mode and one is transport mode. Or you can say, yeah, the tunnel mode and the transport mode. In this tunnel mode, there are two types of mode. One is main mode and the other one is aggressive mode. So what all are the differences here? In main mode, actually they use 6 type of messages. In aggressive mode, they use 3 types of messages for the negotiation. So that is what we are going to discuss. I believe you guys have a little bit background about the the modes, but anyways we will be seeing this in detail also, right? So let me first create a topology also, because as of now the topology is not there. Or let me see if we have already open project. Yes. Let me see if I'm able to open this. Looks like yes. Okay, not sure what exactly this is, but I will be having another one also. Just one moment. MPLS, Ipsec, okay. It seems nothing is there, is it? Okay, we can make the topology, no problem. So I'm not going to take more than 3 routers. So let's set it up. You can use serial interfaces, but here we'll not have the serial interfaces. We can use okay, you can use serial interfaces. 9/0/1/2. So here we can use anything. It's part of configuration. So let's say here what you are using 140.1. maybe 14.0/24. just an IP schema, anything you can use. 24 and 34. Over here between this is going to be a cloud. The R4 is going to be a cloud here. Okay, I'll put it this way. So let's configure the routers. So I'm just making the topology ready for the labs. Okay, it's a little slow. Okay, so interface 00 slash, yeah, interface 01/0 140.1.14.1 shut down interface loop back 0 1.1.1 0. I will configure a default route because to reach the different networks. So IP route towards my gateway 140.1.140.4. 14.4. So that's I'm done in R1. I'll configure R2 also. Interface 01/0. IP address 141.24.2. 0. No shutdown. Interface 2.2.2.2 and IP route 140.1.24.4. Configure R3 also quickly. Interface 0 IP address 140.1.34.3. No shutdown. Interface loopback 0 and 0. IP route 140.1.34.4. 0.0.0.0. Default route. Let's go to R4. Interface CL1/0. IP address is 141.1.14.4. And no shutdown. 7/1. So 24. No shutdown. And 1/2. 34.4. And no shutdown. So I should be able to now ping our as a 34.3. It's like or 14.1, 24.2, 3403. All right. So we have the reachability. Yeah. All right. Now our objective here. Let me again go with the task. Configure basic site-to-site IPsec VPN to protect traffic between IP address 1.1 and 2.2 using the following policy. So Issac, what we have to use here is authentication as in pre-shared, encryption as in 3DES, hashing MD5, Diffie-Hellman group 2, and the pre-shared key authentication. What we have used is champ123. For the IPsec policy, ESP3DES, that is for the tunnel 2, and hashing MD5, proxy ID 1.1 to 2.2. This proxy ID means interested traffic. Okay, so a little bit about this. Issac Internet Security Association and Key Management Protocol is defined, okay, and it is framework which defines the following: procedures to authenticate a communicating peer, how to create and manage essays, key generation techniques, and threat mitigation like denial of service and replay attacks, right? So Issac does not specify any details of key management or key exchange and is not bound to any key generation technique. Inside of Issac, Cisco uses Oakley for the key exchange protocol. Oakley enables you to choose between different well-known Diffie-Hellman groups. Issac and Oakley create an authenticated secure tunnel between two entities and then negotiate the SA for IPsec. Both peers must authenticate each other and establish shared key. So I'm not going to anyways read out the entire thing, but this is what we have discussed, in theory as well. So yeah, I'm just scrolling it up so that you guys can, offline, you guys can go with this. Uh, I would like to discuss this because something here we haven't discussed. So Issac IKE phase 1, two Issac peers establish a secure authentication channel. This channel is known as the Issac SA. There are two modes defined by Issac: main mode and the aggressive mode. What we are doing is the main mode. So IKE phase 2 SAs are negotiated on behalf of services such as IPsec that needs keying material, and this phase is called quick mode. All right, so in Issac phase 1, two modes. We have one mode, aggressive mode, and then the main mode. In Issac IKE phase 2, we have one called quick mode, right? To configure IKE phase 1, you need to create Issac policies. All right, so this we'll discuss while going to the configuration. All right, so let's go with the configuration. So let me also open one document which is, very good in terms of the configurations and all. Just hold on. So while configuring the all right. All right. So if you see this document, So while configuring actually the site-to-site VPN between two NPS, these are the 5 things that we have to make sure. Okay, so first what we have to do, configure the parameters for phase 1, then configure the parameters for phase 2, then define the traffic that will be encrypted over tunnel, configure a crypto map to link the above parameters to each other, and then last but not the least, apply the crypto map to the outgoing interface. Okay, so let's go with the first, configure the parameter for phase 1, and then probably I'll copy the commands here also. All right. So in order to configure, what was the task? It says that the authentication should be pre-shared key. But in phase 1, what are all things that we have to configure? We have to configure the authentication. We have to configure the confidentiality, Diffie-Hellman group, and hashing, isn't it? So these are the things that we have to create. So in order to create that, crypto Issac, because in phase 1, what is the protocol? Issac is a protocol that is going to work. Policy, and give the tag of this. Anything. So crypto Issac policy 1. Under this, I have to define encryption. What, as per the task, it is asking to configure 3DES encryption. Encryption 3DES. Hashing. As per the task, for the integrity, MD5. Authentication, these are the methods, pre-shared, RSA encryption, and the RSA signature. We are going to use pre-shared key, PSK, pre-shared. And in order to mention the Diffie-Hellman group, these are the groups actually, 2, 5, 24. So more actually, if you see here the 19 or the 24. So here we have 2048 bits. Okay, if I put 2, so 1024 bits. So I'm going to use anyways group 2 as per the task, right? The do show run and section crypto. These 5 things we have configured, and let me put it in the also. Phase 1 is not yet done because I have configured here the authentication as in pre-shared. So I have to also define the authentication, isn't it? So in order to define the authentication, crypto Issac key and champ123 address and 10.1.24.2 means whenever I am communicating with this particular IP host or the peer, I will use this pre-shared key champ123, which means whenever I'm accepting the packet from this, also it should come with this particular the same key. If it is coming with this with different key, then it is not a valid. This is now where the phase 1 is done. This is where the phase 1 is done. Now the second is configure the parameters for the phase 2. Okay, so in order to configure the phase 2, crypto IPsec, because Issac what we used for the phase 1, now crypto IPsec. And in order to configure, I don't have to configure here the authentication because authentication is already being configured in the phase 1. So here I have to define two things, hashing and encryption. Okay, so transform set, the name of the transform set could be champ, and then what all are the encryption. So encryption, as per the task, they are saying ESP is the protocol here. ESP is the protocol for the phase 2, which will, in order to set up the phase 2 tunnel. And along with the ESP, it is 3DES. That's what 3DES. And this is the hashing. So as I told you, in phase 2, you have to define only two things, encryption and then hashing. Right? So I'll say ESP MD5 HMAC. So for phase 2, I'm using this encryption and this hashing. Now remember what all configuration you have done in this peer, phase 1 and phase 2, exactly it has to be same in the other peer also. So if here I'm using 3DES, there also I have to use 3DES. From here I'm using HMAC, MD5 HMAC, so there also I have to use HMAC, MD5, not the SHA or something. Same goes for the phase 1 also. Clear? All right. What's the third? The third is define the traffic that will be encrypted over the tunnel. Okay. Define the traffic that will be encrypted over the tunnel. So as per the task, if you remember, it says when 1.1.1.1 communicates with 2.2.2.2. So in order to define that, I have to create an access list. Access list 101 permit IP host 1.1.1.1 when the 1.1.1 is source and destination is 2.2.2.2. Right? So this is the third step. Let me again go back to the, so first was configure the phase 1, which we have configured here. Second is second is configure the parameters for phase 2, which we have just now configured. Let me just copy it. So it's here, and then configure the interested traffic, define the traffic that will be encrypted, so access list. So as of now, what all three things we have configured, it is separate. There is no link between them. Means the step 1, step 2 and step 3, there is no any link, right? So in order to apply all three together, in fourth, what it says, configure crypto map to link the above parameters to each other, right? So let's configure the crypto map, and could be CMAP. And then the sequence number, anything you can give. But here I have to say, I want to enable Ipsec and Issac both together. Issac for phase 1, Ipsec for phase 2. So this new crypto map will remain disabled until a peer and a valid access list have been configured. Now in this, what access list we have configured? So I'll say first set peer. Means who is going to be peer? Peer is 140.1.24.2. Okay, means I'm applying it on the above what we have configured before. Set transform set, the phase 2, and the name of that is CHAMP, I believe, champ. Let me quickly check it out. Yes, champ. And then match access match IP address. What's that? Match address. Okay, 101 means match that access list also. So in this fourth, I have applied what all we configured in the 3 steps. Here in the fourth, I have applied together everything. Last but not the least, I have to enable it on the interface, which is the fifth. So we'll go under interface serial 1/0 because the interface is serial 1/0. Okay, we'll say crypto map, and we have configured CMAP, crypto map, right? That's enabled. You will see the message crypto Issac on, Issac is on. So that is the configuration which we have configured in R1. Now the same thing, what I'm going to do is I'm going to add this to the fourth, and just, you know, set peer and match this, and interface, so that I don't have to, you know, configure there as well. I will just have to, you know, configure it. That's all. Access list we have created. All right. So what I'll do now is sorry, I have shared something else. Okay, hold on. Okay. So as you see here, this was our phase one we have configured. So I'm going to change now because I'm going to configure in R2. So for R2, it will be 14.1. Rest everything is going to be same. In phase two, this is going to be same. IP address, this access list is going to be like 2.2. And then host 1.1.1. And here also it will be 14.1, remaining everything same. What I'll do, I'll just copy it, access list 14.1, copy it. Let's go to the terminal, R2, and paste it. So I guess I didn't receive any error message, which means everything has been configured. Yep. Is that okay? Is that clear, guys? Cool. So now the verification part. Okay, so in order to verify, let's perform some debugging to see what's exactly, you know, happening, or what's exactly happening when the IPsec tunnel establishment happens. So there are two commands, the debug commands, that you can use to actually see what is, you know, going on and who is your interested traffic. So one is debug crypto. So let me go to R1 first. So debug crypto Issac. Okay, and debug crypto Ipsec. So these are the two actually, you know, debug commands that we can. And I'll also enable here in R2 so that we can check it. Debug crypto Issac and debug crypto Ipsec. For the verification, as you see here, show crypto Issac SA. This is to check, this command is to check the phase one. As I see, I don't see anything over here. And show crypto Ipsec SA. As of now, I do not see any packets encapsulated, decapsulated, encrypted, digested, nothing. It's zero. though it is showing here the IP addresses, but nothing is happening because it is enabled on this. Okay, so as I told you before, if the phase 1 doesn't come up, then there is no chance of coming phase 2 up. So first phase 1 has to come. So phase 1 has to come or will come only when we have the entrusted traffic. Enabling the crypto map IPsec on the interface, that doesn't mean that this when they'll start or the tunnel will be negotiated. No, the tunnel will be negotiated only or established only when the entrusted traffic goes from from any of the peer. So in order to do that, what I have to say, I have to ping 2.2.2.2. Okay, but the question is, if I ping this way, will that be IP reachability? Because as of now, this 2.2, fine, R1 knows because R1 is having default route. Show IP route static. It is having default route, so R1 will send it. But when it comes to the transit network, when it comes to the service provider, R4 doesn't know where is it, isn't it? So I may have to actually configure IP's static route. Exactly this, and 140.1.24.2 and 140.1. Otherwise the traffic will be broken, right? All right, now what I'll do is, let me ping 2.2.2.2. okay, it's pinging. I do not see anything in the crypto map. Do I have to put it in the source loopback? Show crypto Issac camp SA. Nothing is there, which means ping from source loopback 0. First packet you will see is dropped. We'll discuss about this. And in fact, the reachability is not there. Something is wrong, I believe. Again, it's not, but if I check SA, no, it's not there. 1 and 2, 1/0 and 1/0. Okay. Have we configured in R2 access list? Just wanted to verify the configuration. Anyways, that's fine. As I can champ 1, 2, 3, 10 address, 10.1.4 and 1. Oh, my bad. My bad is because, let me show you this. Because here what I have configured, it is 140. Okay, 140 dot. So this, okay, let's go to the CLI and configure in R2. Show run section access list. That's fine. Let's show run section and crypto. So in this, what I have configured is this, which is not correct. So it should be 140.1.14.1. This is the IP address we are using. And then this is fine. Let me also verify in the show run section crypto. Okay, that is why that's the mistake, because there is no peer with this, right? So 140.1. And then remaining everything is fine. All right, so let me again initiate ping. Yes, I see that the ping is successful. Okay, all right, can you stop it now and debug all? Anyways, it is complete. So now if I check the Issac camp, you see here 24.1, 14.1 source, QM idle, and connection ID is active, status is active. State should be always QM idle if it is working. That is the phase 1. And to check the phase 2, show crypto IPsec SA. Now you see the packets encapsulated 4 because I sent 5 packets, but one got dropped to bring the tunnel up. 4 packets encrypted, encapsulated, and digested also. And the same decapsulated, decrypted, and verified. In this local crypto endpoint is 14.24.2, and this is what we were talking about, SPI, the security parameter index, kind of the king, but it will not show the session ID. This is kind of a session ID, you can say, but it won't show any other details in this. This is the tunnel mode, because we were discussing about there are 2 types of mode. One is tunnel mode and one is the transport mode. This is a tunnel mode where we are using for the phase 2 we are using 3DES and MD5 HMAC. And this is the outbound anyway. So yep, this is outbound, and that one is inbound, SPI. Right now, since it is main mode, in main mode there are 6 types of messages which are exchanged between 2 peers in phase 1. Okay, so let's see in the debug command also what all those 6 type of messages. Okay, so the first packet triggers here, as you see. Where is that? Okay, here the first packet which is dropped. Okay, somewhere we'll see type sequence about packet this sent with the source. The first packet is dropped. Okay, so it means the ICMP packet triggers Issac process, as this is our interesting traffic matching our ACL. So before actually start sending IKE packets to the peer, the router first what it does is checks if there is an any local security association. Right, once it checks matching that traffic, so once it checks that, right, it will check against the IPsec SA, not the IKE SA, just remember. So it will only check the against IPsec SA. So if okay, then no SA means there must be IKE packet sent out, right? So in this SA request, you can see here somewhere IPsec SA request, security association request, right? So the router has tried to find any IPsec SA matching outgoing connection, but no valid SA has been found in security association database. So might be you will receive some in first packet itself, SA request profile. Okay, SA request sent. SA, yep, SA request profile is null. Means this means the router has tried to find any IPsec SA matching outgoing connection, but it is not valid. Why? It's because the first packet got dropped, right? So no valid SA has been found in security association database. Okay, now coming to the IKE phase 1, in phase 1 main mode, message number 1. So by default what happens, IKE main mode is used, so we should expect 6 packets, right? In phase 1, 6 packets are being exchanged. So there is a message saying that aggressive mode cannot start. So as you see here, cannot start aggressive mode. In this somewhere it will be cannot start aggressive mode. This is the first message type. in main mode phase 1, this is the first message type. Cannot start aggressive MAC trying main mode. So this means, okay, that there is a message saying this particular aggressive mode cannot start means. However, it does not mean that there is some error. So that doesn't mean that there is an error. It just means that aggressive mode is not started. That is why we are using, or you can say the aggressive mode is not configured in the local router. That is why we are using the main mode, right? Then the router checks Issac policy configured and sees that there is pre-shared key authentication configured in this. So as you see here, found pre-shared key matching, this one. So it checks, okay, now there is one authentication pre-shared configured for particular this, peer. So pre-shared key again for the remote peer has been found. Issac will use it to authenticate the peer during one of the last stage of the IKE phase 1. Okay, now you will see somewhere sending packet, this one, sending packet to particular this my port 500. So Ipsec actually or Issac they use port number 500. So if there is a firewall, it should be allowed. And so the router initiating IKE exchange is called the initiator now. The router R1 here is the initiator. The router responding to IKE request is called the responder. So here R1 is initiator because it is initiating, and R2 is the responder. Okay. So now R1 is sending actually Issac policy along with the vendor specific IDs, which are part of IKE's packet payload. MNNO state also you have seen at the end of this indicates that Issac SA has been created. No state means here this one. No state means the Issac SA has been created, but nothing else has happened yet. As of now, nothing happened. It is just the state has created. Now that was the message 1. Okay. Now let's check it out, the message 2. So in again IKE phase 1 main mode message 2, you will see somewhere received packet, this one. So received packet from port number, so destination port, source port, global, no state, right? So this means, so actually what happens, so seems everything is going smooth because we are seeing the second message. We have got response packet also from the peer, and this is the first place where something could go wrong. And this is most common issue when configuring VPNs also. Means if something is wrong, right, so it will tell you here itself. The received packet contains SA chosen by the peer and some other useful information like vendor IDs. Okay, so those vendor specific payloads are used to discover NAT along the path. So if you're using NAT, maintain, keep alive, DBD, the router matches Issac policy from the packet to one locally configured also. If there is a match, the tunnel establishment process continues. But if there is no match, maybe encryption on all those, then it will drop it here itself. So if the policy configured on both the routers is not the same, as I told you, the cross-check process fails and the tunnel is down. Okay. So now received packet from 10.12 in this 24.2 means the responder has responded. Now process SA payload message ID 0. Okay, you see the processing vendor ID we were talking about. Vendor ID seems union DPD but measures extending mismatch. Vendor ID this NAT So this is what actually we did discuss in this particular message number 2, or if everything is fine. So processing SA payload, processing vendor ID payload, checking Issac transform 1 against, where is that? This one, checking against priority 10 policy, because the policy what we have created is 10, and these are the parameters we have configured. Okay, so now this means these particular options are acceptable. Next payload is 0. So the router is processing Issac parameters that have been sent as the reply. Vendor IDs are processed to determine if peer supports, a NAT or traversal, dead peer detection feature. Issac policy is also checked against the policies defined locally. That is where we have seen the encryption, Diffie-Hellman group and all. ATTS are acceptable indicates that Issac policy matches with the remote peer. Means what are locally configured, it is matching with the remote peer configured, with the locally defined policies starting from the lowest index. Okay, so that was the phase in phase 1 in main mode, message 2. Now the message 3 is somewhere sending, you should see with the sending again, this one, sending packet 224.2 my port this, but this time NMSA and setup. Earlier it was no state, but here now it is setup. This is the message 3 in main mode. Remember we were talking about 6 messages. This is the 3rd message. Okay, so the 3rd message is sent out containing IKE, key exchange for IKE, information for Diffie-Hellman secure key exchange process. In message 4, 4th message has been received. As you will see, received packet, this one. This is the 4th message. So the 4th message has been received from the peer, which means, and this message contains KE, key exchange payload, and based on that information, both peers can generate a common session key. Now, based on the above information, both the peer, what they will do is they will generate the common session key to be used in securing further communication. So the pre-shared key configured locally for the peer is used for this calculation. So what I have configured, the pre-shared key, in this case champ123, will be used for the, the calculation. And based on that only they will create the session key. We have seen SPI, right? The session parameter index. It will not contain any, sensitive information, but it's kind of, the session key itself, you can say. So after receiving this message, peer can also be able to determine if there is NAT along the path. Okay. So here MMSA setup indicates that the peers have agreed to on parameters for the Issac assay. Earlier we exchanged Ipsec assay, now Issac assay. Same processing, KE, payload, vendor ID, NAT, pre-shared key. Speaking to another iOS box. Okay, coming to the 5th message. That was the 4th. Coming to the 5th message. So 5th message is used for sending out authentication information to the peer. This information is transmitted under the protection of the common shared secret. So as you see here, SA is doing pre-shared key authentication using ID type, ID IPv address. And the address is 12 in this 14.1. Okay, and sending packet here key exchange, key exchange. So key exchange means indicates that the peers have exchanged Diffie-Hellman public keys and have generated a shared secret. The Issac SA also remains unauthenticated. Note here that this process of authentication has been just started. As of now, authentication hasn't happened. Now it is started because now this is where they are exchanging the key, sending IK IPv4 packet. Okay, and this is the message 6 received packet, means the authentication is successful. Message 6. Okay, so the peer identify is verified by the local router and SA is established. Phase 1 SA is established. This message finishes Issac main mode. So main mode is also done here, and the status is changed to IKE P1 complete. We'll see somewhere here IKE P1 complete. So SA authentication is stated authenticated and IKE P1 complete. Now note that the process of peer authentication is still in progress. Okay, just remember NM key exchange. Remember that there is also one IKE main mode state which is not visible in this debug output. All right, so it is called NM key authentication, NM key auth, which indicates that the Issac SA has been authenticated. As you see here, we have seen already though in this. Where is that? Issac received, and this one authenticated. Okay, so if the router initiated this exchange, this state transitions immediately to the QEM idle and a quick mode exchange begins. So that is where we have seen under this show crypto Issac SA QM idle. Now the quick mode means the phase 2 begins. So QM idle and the quick mode exchange begins. Okay. So that is called the in main mode. In phase 1 main mode, 6 type of messages. Now let's talk about the quick mode in phase 2. Now phase 1 is over. Now talking about the phase 2 quick mode, message 1. Have you seen somewhere? We'll see somewhere here. Okay, where is that IKE complete? Where did we see that? Okay, over here. Now you see beginning quick mode exchange. So now it's time for the phase 2, which is a quick mode. The router sends out the packet containing local proxy ID, means 1.1.1.1, right, by the IPsec tunnel, and security policy defined by the transform set. So as you see here, sending packet, this is the in quick mode message number 1. There are 3 messages in quick mode. Sending packet to this, my port this, and then QM idle. Okay, this is message number 1. Message number 2 is the second QM message, is a response from the peer. So received packet, this is message number 2. Received packet from 140 this, destination port, source port, global, QM idle. Okay, so this state of IK is QM idle. This indicates that the Issac SA is idle. It remains authenticated with its peer and may be used for subsequent quick, mode exchanges. It is in and kind of, the quiescent state. Checking IPsec proposal 1, transform 1, ESP3DES, tunnel mode, HMAC MD5 authentication. All right. So the routers are now negotiating parameters for the IPsec tunnel, which will be used for traffic transmission. which will be used for traffic encapsulation, packet encapsulation. These parameters over here are actually defined by crypto IPsec transform set command what we have configured. Okay, so note that lifetime values of IPsec are variable. Okay, the life we have life SA life duration, right? It is variable. At this moment, you are able to set it both globally or the crypto map entry. At the last, ATTR acceptable. Where is that ATTR acceptable? Somewhere we'll see here. This one means that IPsec parameters defined as IPsec transform set match at both sides. So why we are discussing all those in detail actually, so that in case if you are troubleshooting, you can go by message in phase 1, message by message in phase 2 also, and check it out what is wrong with this. Okay. Local, here you will see here the local proxy and then the remote proxy also. So this is the access list we have, what we have actually specified the entrusted traffic between 1 and 1.1 and 2.2. So the local and remote proxy are defined. This indicates source and destination set in crypto ACL, which defines the entrusted traffic for IPsec tunnel. Just remember that the crypto ACL at the both side of this tunnel must be mirrored. Means it should be exactly what you have configured here. So if it is here source, there should be, and destination, there it should be source and destination. Otherwise it will be invalid proxy ID. Now creating IPsec essays. Do I see somewhere? Okay, after this, and then old find IPsec. This is again the parameters. Map. I don't see actually map found. It's map. Okay. Crypto map proxy match. That's fine. Processing and transform set. Authentication remote lifetime. Okay, match this one is done. Processing this old state. Okay, processing ID node input this IK exchange old state is this. Crypto mag got a Q event. So that is where you see the source address 1.1 and 2.2. Crypto map proxy match. I'm sorry. All right. So let's go for the third message, IK quick mode, phase 2, third message. The last message, which is third, finishes QM. Upon completion of phase 2 IPsec session, key is derived from new Diffie-Hellman shared secret. So this session key actually will be used for encryption until IPsec timer expires. So if you see here, sending packet will be somewhere IPsec span exchange. Not this. Here itself we will see somewhere received. Sending packet. Okay, reconnecting with this IPsec map found. Where is the message 3? received packet from this. Okay, sending IK packet QM mode exchange. Maybe in this debug actually it is not there, but the third message is something. It should be IPsec created map. Okay, match proxy IPsec reconnected. Okay, this is match proxy IPsec. Should be node input IK message from peer IKQM exchange, old state IKQM1, new state IK find, got a QA event IK message, proxy match. So here it should be, but anyways, there has to be, before this, they actually exchange the information also. It is not showing here though, but it will be like again the QM idle itself. So the QM idle itself again means the Diffie-Hellman group, you know, the keys has been shared, the secret. You will see IKEM QM1, new state is IPsec install fine. You will see also the reconnect fine that IKE2 has started. Okay, this one I was talking about. I'm sorry. Sending packet to my code. This QM idle. This is the you know, IKE phase 2 message 3 quick mode. And old state was IPsec install await. New state is IKE QM phase 2 complete. So this indicates that the phase 2 is complete. Right. So that is how actually you will, you know, see the messages step by step if you enable the debug, and if you are facing any issue while establishing this side-to-side VPN between two endpoints. Okay, so that is how we complete the task 1 with the full detail of all 9 message types, 6 in the main mode phase 1 and then 3 in the phase 2 kick mode. All right, we'll continue with this tomorrow. We'll do aggressive mode tomorrow. Do we have any question, guys? All right, thank you.
You'll share